Hello everyone and welcome to PC Retro Tech. In today's video I'm going to be talking about how to draw vertical lines on the screen. So I previously uploaded a CGA Graphics Demo on the channel, and in that we had a section where the screen gets filled by drawing vertical lines from the top to the bottom of the screen. And I mentioned that I'd written a code in assembly language which will draw arbitrary vertical lines, so starting at any y0 value and going down to any y1 value, so y coordinates y0 to y1. So this is the function for doing that, and all of the code is on GitHub, and there's a link in the description. So if you think about what a vertical line does, it draws all the points with a given x value from a starting y value to a finishing y value, so y0 and y1, including the endpoints. And we're going to draw all of the points in the same color, and that'll have the value color that we pass into this function. So I previously talked about how to draw pixels on the screen, so I'm not going to discuss that in this video. But we don't just call the pixel draw function, we try to pull out as much of the code as we can from our inner loops so that we don't repeat the same thing over and over and we just do it once outside the loop. So that's the main idea of this function. And of course we want to make this as fast as possible. So the first thing we do after saving some registers is we compute the segment register, well that's B800 in hex, and we put that into the ES register. So the ES will be the segment of the screen memory. And then we have to do a calculation involving the y0 coordinate. So there are two things that we compute. We compute y0 plus 1 on 2 and y0 on 2. And I'll explain in just a moment why we compute those values. So the first thing we do with these two values is we multiply them by 80. So you'll see a little bit further down here we also multiply y0 on 2 by 80. So we're using our standard trick which I've talked about in a previous video for multiplying by 80. You first multiply by 16 and then you multiply by another 4, so that'll be a total of 64. And 16 plus 64 is 80. So you just add 16 times the value plus 64 times the value, and that'll give you 80 times the value. So this is much faster than using the multiply unit in the computer. You just use some shifts and some adds. So the question is, why do I want to compute these two values? And the answer is that they give automatically the offset in screen memory of the first even line and the first odd line that we want to draw on, that we want to draw a pixel on. So remember that the screen memory is laid out with all of the even lines first and all of the odd lines after that. And their odd lines start at offset 8192, which is why we have this 8192 here. So let's try and work out why this formula gives us the first even line offset. So remember, y0 is the first line that we want to draw, and it might not be even, it might be odd. So let's go through two examples to show that this really gives us the offset of the first even line. So first of all, if y0 is even, then adding 1 to it before we divide by 2 doesn't make any difference. So for example, let's suppose that y0 was 2. Add 1 to it would make it 3. When you divide by 2, you still get the same quotient, 1, and the remainder gets thrown away. So the adding 1 here doesn't affect things if y0 is even. If it's odd though, imagine y0 was 3, adding 1 to it would make it 4, and then when we divide by 2, we would get 2, which is different to what you get if you had y0 divide 2 here. It's 1 more. So I claim that this formula gives us the offset for the first even line in screen memory. So obviously the number of even lines on the screen is half the number of lines, and so you have to divide by 2 somewhere, so that's obvious. But why does this give you the offset of the first even line that you want to draw? Well, if y0 was, say, 2, then the first even line that you want to draw is 2. But if y0 was 3, then the first even line that you want to draw is 4, because 3 is not even. So that's why adding this 1 here is important when we want to compute the first even line that we want to compute. The same is true for this formula here. This will give us the offset of the first odd line in memory. The 8192 will take care of the fact that it's an odd line, and I won't go through the 2 different cases, but it doesn't matter whether the first line that you want to draw is even or odd. This will then give you the offset of the first odd line. So those are the 2 values we've computed so far. The next thing that we do is we take the y1 coordinate, which is the last line that we want to draw, and we divide that by 2. And it turns out that this will give us the last even line that we want to draw. It doesn't matter whether y1 is odd or even, this will always give us the last even line that we want to draw. So this is not quite enough information. We might also want to know about the last odd line that we want to draw, but it's going to turn out that we don't really have enough registers to store this information. So we can save half a register by storing some extra information. So whether or not the last odd line that we want to draw is after the last even line that we want to draw depends only on whether y1 is odd or even. So this information we can store in a single byte, and we do it by storing the value 80 if y1 is even and the value 0 if y1 is odd. And this little sequence of instructions here is for computing that value, and we store it in CH. So we'll come back to this value CH later, but basically it's just going to allow us to get from the last even line to the last odd line, and we can do that without using an extra 16 bits. So I'll come back to this later. Just remember for now that this value 80 if y1 is even and 0 if y1 is odd gets stored in the CH register. So we'll pull it out of the CH register later and use it. So we've now computed 3 different things. We've computed the first even line, the offset of the first even line, that is, the offset of the first odd line, and the offset of the last even line, and we've computed, of course, this additional auxiliary information. Alright, so that brings us down to here. This is just multiplying by 80 using our standard trick. So we've dealt with the y coordinates. Now we need to deal with the x coordinate. Remember, the x coordinate of all the points we want to draw is the same. And we need to compute the byte offset within a line of the given x coordinate. Remember that there are 4 pixels per byte in a line, so there's only 80 bytes per line on the screen, and the way that we compute the byte of the pixel at coordinate x, the offset of the byte within the line that is just to divide the x coordinate by 4, and so that's what these lines here do. So once we've computed which byte offset within a line corresponds to coordinate x, we add that offset to each of the 3 values that we've computed so far. So the offset of the first even line, the first odd line, and the last even line. Alright, so the next thing that we need to worry about is the color. So I'm not going to go through the color stuff again because I went through it in a previous video, but basically there are just 2 things that we need to compute, and that is the bits, the 2 bits corresponding to the color shifted into the right location, because there are actually 4 pixels in each byte, and we need to make sure that we set the right 2 bits. And we also need to compute a corresponding mask. So those 2 things are computed here. So AH will end up having the color information, and CL will end up having the mask. There's one other thing: we store the value 79 in the SI register. The reason for that is when we're drawing our lines, when we're drawing our pixels on the screen, we need to jump by one line each time. First we'll draw all the pixels on all the even lines, and so that'll mean jumping one line at a time in screen memory, in the part of the screen memory that corresponds to the even lines. And jumping by a line means to jump by 80 bytes, because each line is 80 bytes. But it will turn out that we'll have already jumped by 1 byte automatically in the code below, and that'll only leave 79 bytes that we need to jump for each line. So I'll come back to that later, but for now we're just going to store this value 79 in SI, and then we'll be able to use it later. Alright, so here's where all the real work gets done. We first draw all the even lines on the screen, so all the pixels on even lines, and this is done with this loop. So it starts here at vline even, and it ends with this jump instruction, which just loops back around. Of course, this loop will just continue forever if we don't jump out of it, and there are two places that we can jump out of this loop. There's here and there's here. So basically all we do is we compare the current offset, which is DI, that's the offset that starts as the offset of the first even line that we want to draw, and compares it with the last even line that we want to draw, the offset for which we put in DX. And if we're already past that point, then we stop, we go to done even. So that's done twice in here. So why is it done twice? Well, the reason for that is that this loop doesn't just draw 1 pixel per iteration, it draws 2 pixels per iteration. And the reason for that is that jumps are very expensive, and we want to maximize the amount of work we get done with a jump. And the way to do that is to unroll the loop, and so that means just do the same thing twice. And we're unrolling by 2 here, so we're drawing 2 pixels, not 1, for each jump. So other than that, the code here is exactly the same as for drawing a pixel. You basically AND the value that's in the screen memory already by the mask, and you OR with the color information corresponding to the pixel that you want to draw, and you write that byte back into screen memory, which happens when you call the SOSTB. It writes to ESDI, it writes the value that's in AL into ESDI, into the memory address ESDI. And the other thing it does is it increments DI by 1. Well, that's okay, we want to increment DI anyway because we need to add 80 bytes to go to the next line. So if we've already added 1, then we just need to add an extra 79 to DI to get to the next line. And remember that we stored the value 79 into SI. So that's basically all there is to it. There's just 2 pixel writes into screen memory using SOSTB. And of course, we check after each pixel that we draw whether we're done. And if we're done, we jump down to done even. Alright, so next thing we need to do is draw all the pixels on odd lines. So that's what this loop does. Before we can do that, we need to compute the offset of the last odd line. So first of all, we put the offset of the first odd line that we need to draw into DI, and we computed that previously, so that just goes into DI. And then we need to compute the offset of the last odd line. But remember I said that we didn't have enough registers to store that value. Instead, we stored the offset of the last even line in DX, and we stored this extra auxiliary 80 bytes, which will be 80 if we need to do an adjustment to go backwards from the last even line. It might be that the last line is even. In that case, we definitely don't want to draw an odd line after that. We want to stop at the odd line before the last even line. and so that would mean subtracting something from dx if the last odd line that we want to draw is before the last even line. Otherwise, we don't want to subtract the value. And the value that we have to subtract is 80 or 0, depending on which of those two cases we're in. So that's what this is for, and then this is the loop for drawing all the pixels on odd lines, and it's exactly the same as the loop for drawing all the pixels on even lines. We start with di equal to the offset of the first odd line we need to draw, and the comparison that we do is to tell whether we're done is to compare with the offset of the last odd line that we want to draw, which is what we just computed. Notice that to compute that value dx here, we had to add 8192 because the offset of odd lines is 8192 after the offset of the even lines. And the way to add 8192 to dx really efficiently is just to XOR the high byte with 20h. So that's what this is all about. This is just adding the 8192 basically. We know that that bit's already 0 for even lines, so we just make it a 1 for odd lines. So that's really all there is to it. Otherwise, the structure of this code is exactly the same. That draws all the even lines in a loop, and then we just pop all the registers that we saved for the compiler and return from the function. So let's just summarize what we did in this algorithm and why we did it. The main two tricks here are that we draw all of the even lines first and all of the odd lines second. All the pixels on the even lines first, and all the pixels on the odd lines second. And the reason we do that is it saves us having to add and subtract 8192 all the time to jump between odd and even lines. By drawing all the even lines first, we just have to jump by 80 each time, and we don't have to go backwards and forwards between two values, and it's just a lot easier to do the arithmetic. So the second optimization that we did is with this unrolling by 2. So in both our even line drawing loop and our odd line drawing loop, we drew 2 pixels per loop, and that just saves a little bit of time. All of the other calculations that we did are kind of irrelevant because they're only run once. The only things that are run many times are in the loops, and you can see that these are very short loops. By doing all of that pre-computation first, that saves a lot of time in the loop rather than just running a calculation for each pixel over and over and over again, which would be very expensive. We do as much of the computation as we can outside the loops and then have really short compact loops. So that's basically it, guys. I'll stop there. If you enjoy this kind of content where I explain some assembly language for doing CGA graphics, then please give the video a like, and that'll let me know that you want to see more of this style of content. And if you like the video, consider subscribing to the channel. We have videos on assembly language and C programming for graphics for old retro hardware, and we also have lots of interesting videos about old retro hardware, and I show off the retro machines that I have. So if you want to see more of that sort of thing, subscribe to the channel, and don't forget to put the bell icon on so that you get notified when the next video comes out. Thanks for watching, and we'll see you in a later video. Bye!